get from this Chern class. Okay, got it. And so, as you know, the top Chern class, when you self-intersect C1 to the dimension of the variety, then you get the self-intersection of canonical class plus minus 1, and you go all the way down to Cn, which is the topological Euler characteristic of X, and there are numbers in between. If you take a partition, so all partitions participate on the numbers that you can get from these Chern classes. For surfaces, you will have 2. Okay, so this is the parenthesis before going to surfaces. So this talk is about dimension 2. There is some initial picture for dimension 3, and you can check a very nice paper that surveys dimension 2 and 3 by Bruce Hunt, which is like a big exploration of what we know, what we have for threefolds, and not much progress after that, I think, we have made. But also you have a lot of works by Meng Chen, Yungai Chen, others, like Heikon also, I think this is there, on restrictions for these invariants, for Chern numbers, for threefolds. And also take into consideration that now for threefolds, we might consider minimal models, which, as you know, might be singular, etc. Is a different world there. There is more difficulties. And I know about that because I have a PhD student, Jerko Torres, which is working now on this threefold geography and asymptotic invariants. So I just wanted to mention that parenthesis on that dimension. Dimension 4 and other dimensions, I don't have any work in mind. Maybe there are none, I don't know. So let me recall you the dimension 1, which is trivial. So in dimension 1, you have C1, the only Chern number, and that is minus the degree of canonical class. So as you know, 2 minus 2g, which is the topological Euler number for these Riemann, compact Riemann surfaces. And so you can think about it as just the genus. So general type means genus bigger or equal than 2. And then the geography is very simple. So for each genus, you need to have a curve. And here I solved it. So that is the curve. So there is no, that is a very particular curve, but that is existence of a curve of that genus. And the topology for each case is fixed. And so the fundamental group. Dimension 1 is very, very simple in terms of geography. When you pass to dimension 2, there is a dramatic change. And the goal of this talk is to tell you about this dramatic change. If you have any questions, please interrupt me. I will check the chat. This talk is going to be short. I want to have questions. Let me move this chat here. Okay, so there is a dramatic change. Say first that I will talk about that. So say first that I consider curves in surfaces. So this means a pair of a surface and a divisor, like log geometry if you want. But even in the simpler case, which is configurations of lines in P2. So this is very simple to explain. What I mean by a configuration of lines, I mean that, for example, there you have 6 lines in general position, only nodes at singularities, but this, of course, could be degenerated to a very special configuration like that one, where you have 6 lines, but now there are triple points and double points. For me, so D is the number of lines. M point means a point that is exactly in M lines, and Tm is the number of M points. So here you can count 1, 2, 3, and T2 is 3. So 1, 2, 3, 4, T3 is 4. And we have 6 lines. And here there is 15, because it's 6 choose 2. So that is the notation for lines. And then what is the geographic problem here? So Let me explain that. I have a configuration of lines that you see here in P2. And now maybe you have these more complicated points, so we blow them up. So this is blow up all the triple, four-tuple points and not nodes. Now you get this divisor D, which is like the -1 curve over these special points and the strict transform of the arrangement. So this is a simple normal crossing divisor. And now I have a pair, X, D, which is representing configurations of lines in P2. So from where I get the Chern numbers in this case, well, I take the replacement of the chief of differentials, which is the chief of log differentials, where the poles are on D, so omega-1 log D. And from there, I do the same. So I take the dual and then the Chern classes. These are going to be to distinguish between the case of divisor empty and divisor not empty. I put a bar. And so these are the Chern classes. And since we are in a surface, this is a rank 2 vector bundle. We have only 2 Chern classes, and I take the numbers. So C1 square is like the canonical class square, but now the canonical class plus D square. And then C2 is the difference between the topological Euler characteristic. Since this case is very, very simple, we can just go and compute this number. And there you have. So C1 squared is that, and C2 is the other number. Here I point out that we have D, we have the number of M points, and we have the sum. And so for C2. And so the problem is to say I give you 2 numbers, A and B. Do we have an arrangement of lines so that the Chern numbers are those numbers? That is the geography problem. Here I computed for you the numbers in the examples. C1 bar here is 9, and C2 is 6, the other is 5 and 2. Maybe I'm going too fast. Well, we will have more time. Then I want to talk about the restrictions that we have on these numbers, because of course not any number is possible, not any pair. So I can tell you in the picture here for line arrangements is beautiful. I can tell you a lot of things. If A is not trivial, trivial means a pencil, like all lines are passing through one point, or quasi-trivial, which means almost all lines except by one is passing through just one point. So this means except them, this means the general type case, exactly my set of varieties that I like to study. Then we have these restrictions. So you can easily prove that C1 squared is bigger than 0, C2 is bigger than 0, and C1 squared over C2 is between 3 and 2 minus 2 over V minus 2. And this is valid for all ground fields. So it's not only for C. And this is the thing. Here it seems like a Bogomolov-Millau-Callao inequality, but it's not the case. This is completely combinatorial. And it was proved first by De Bruggen and Erdos, 1948. And this is equivalent, this inequality is equivalent to say that the number of special points is always bigger or equal than the number of lines, what I write there. So if you simplify this expression, then you get this. And here we have equality if and only if you have the finite projective plane configuration. So you take all the lines in a finite projective plane over a FQ, Q anything. On the other side, you have that here on the lower inequality, you have equality if and only if the configuration is like a general position configuration. You have only nodes. So the geography problem there is if I give you a pair of numbers, as I said, then do we have an arrangement where those are the Chern numbers? Now that is very complicated, even for lines, and for surfaces it's even worse. But we consider instead exploration of the Chern slope, like the ratio of these two numbers, to try to have a sort of initial big picture of what is going on with line arrangements. Okay, so this is the big picture. Let me explain. This is a big picture. Okay, so as I said, these numbers move between 1 and 3 in any characteristic, 1 and 3. So this is the interval that is allowed for line arrangements. In characteristic P, you really can move from 1 and 3. In characteristic 0, you can move from 1 and 2.6 periodic, which is 8/3. This is 8/3. And this is because now really we have here the Bogomolov-Millão-Callao. This was proved by essentially Hirschenbruch in his famous paper about line arrangements with extra results of Sakai, but then it's not directly the inequality, but you can prove it using that inequality. So 2.6 periodic. And here you have equality if and only if. So say that I never consider the trivial or the quasi-trivial arrangement. So if you don't consider that, then you have equality if and only if you have what we call the dual Hesse arrangement, which is these arrangements of 9 lines and 12 triple points. Only for that one. For 3, you have infinitely many, because it's if and only if you have this finite projective plane arrangement. Now, if you want to go even to the real numbers, then there is more restrictions. Now you can reach only, so the maximum possible is 2.5, which is 5/2. And again, equality, and that is the nice part that you can characterize many things in here. Equality, if and only if, when you have a real arrangement, you have like a triangle, you have a tessellation of the projective plane over R. So you have polygons partitioning the projective plane. This arrangement defines a simplician arrangement, or I have a simplician arrangement if and only if all the polygons are triangles. And it happens that you have equality here, if and only if the arrangement is simplician, which are not classified. This is, well, that is another topic. Also, something that I like to do to have a sort of picture is what can I say about accumulation points of these Chern slopes? And what we can prove is that the Chern slopes are actually dense for any fixed characteristic between 2 and 3. You can prove that they are dense. It's easy to see from the inequality I show you here that you cannot have really accumulation points in between 1 and 2. This is discrete, independent on the field. That is combinatorics. And for characteristic 0, or for the reals, for example, you can prove that they are dense between 2 and 2.5. But the problem here is what happens with the imaginary arrangements, the ones that are really complex. Here we don't know the picture between 2.5 and 2.6 periodic. We don't even have an accumulation point. And what I think that is maybe discrete, as in the left, like discrete here and discrete there. But we don't know. That is open. Now, another thing that I want to point out is that with these Chern slopes, in all situations I know, we always go from low to high. It's like easy to hard. It's like here for general position, from general position to, if you want, finite projective planes or this kind of very special arrangement, simplician arrangement. So you go from easy to hard, like this, okay? So questions that we have there, just to finish with line arrangements, is what is the picture for Q? Actually, here we really need R when you want to, when you prove that this is dense. We really use that they are defined over R. and we don't know if we think that maybe it's possible to be dense over Q, but we don't have really the arrangements to prove that. What we use over R are these simplicial arrangements given by these regular polygons. You know, you have a regular polygon, you can construct a family of infinitely many simplicial arrangements, but there you need to be defined over R after, I think, six sides. So over Q is an open problem, and what the other problem is what is the picture between these 2.5 and 2.6 periodic? Is that discrete over C? So notice that it is not a combinatorial problem anymore, because combinatorially over any characteristic we can move between 2 and 3. There is no restriction there. But over C we can only reach 2.6. We don't even know if there is like an epsilon here where this part is empty. It's hard to handle what is going on there for those arrangements.
Question?
Yes. Yeah.
Do you have, how about 2.5? Can you accumulate to 2.5 from above?
Yes. Yeah. Yeah, we can. And I can give you the example, or I can write it here. You put an N here. These are called Shiva arrangements. And then they go like that, like accumulated down. 2.5. Yes.
Thank you.
Okay, so the moral here is that even in this simplest case, we don't have complete picture. There are many questions. I can mention more. I have no time. Maybe I do. Okay, so static configurations, I want to mention that of curves is and has been relevant for constructions of special surfaces, like the paper I mentioned by Hirschenbruch and many others. This bounded negativity conjecture, as you know, exotic surfaces, so moduli behavior like this Murphy law of Bakil, and many other things. So they are kind of relevant, and I am very interested in configurations of rational curves, not only lines. Even in P2, they are very interesting, I think. Okay, so now the question is, what do we know about the empty for empty configurations? That means surfaces of general type. So I jump to surfaces of general type. So as you know, over C, these are the restrictions. C1 square, so it's the canonical class square is bigger than 0. Well, I'm taking minimal surfaces of general type. C2 is bigger than 0. C1 plus C2 is 12 times the characteristic, the Euler characteristic of OX. And we have the another inequality, which is this, and the Bogomolov-Miyaoka inequality, which is that. And the picture is like that. So here is the Bogomolov-Miyaoka line. This is the nether line. So, and there you have the Horikawa surfaces. This is divided by the Euler characteristic of X. This is 1, 2, 3. You can put it like that if you want. For each point, you have a universe, which is the moduli space for those invariants for surfaces of general type. Even more interesting, you have this Kolar-Sheffer-Barron compactification for each of them. And all of that is very interesting, and I work on that, but I'm not talking about that today. Here at this point, even at that point, we don't have a complete picture. These are the Godot surfaces. We are missing the picture for simply connected Godot surface, or torsion 0, because we don't know if they are all simply connected. Even that point is very interesting. Here you have the fake projective planes. And remember, this goes like this always. Simpler to harder. These are the Ball quotients by the theorem of Yau and Miyaoka, because you need to have canonical class sample. If you have equality here, this is if and only if you have a surface that is a Ball quotient. And they are rigid. very special surfaces over here. Well, that is more or less okay. Now I cannot. Okay, I need to wait a minute. Okay, again, pair by pair. I have like 10 minutes. Pair by pair is hard, although we know existence of surfaces for almost every point. Yeah, I wanted to mention that. We don't know existence of surfaces for all points. There are certain zones in the hard region, like around here, where we don't have even an example. And there are many mathematicians involved, of course, Persson, who invented the term geography, Hirschenbruch, Chen, Xiao, Peters, and many. So again, yes. Okay, so I want to talk about this Chern slope for these surfaces. Now, I will take the slope between 1/5 and 3. So, of course, this is not 1/5, but the asymptotically is 1/5 for unbounded regions. If you take less, then you consider a bounded region. So between 1/5 and 3, this Chern slope is dense, and that is not hard to prove. So in the sense that, and even is more specific, is in the sense that every rational number is possible. But there is no control on any other invariants, and I would like to soon fix some other invariants like the fundamental group. So it's dense, okay, for C characteristic P, you can go to infinity here, and you can prove also that that is dense. So what if we fix the fundamental group, the topological fundamental group? Let me tell you about the simply connected case. Now here again, it's dense, but there is a small story. So until 2014, this region for simply connected surfaces of general type was empty. There was not even an example. And I proved with Rollo that you are even dense in this interval, and that completes the result, and you are dense everywhere for simply connected surfaces. Remember that over in 3, these are ball quotients. So I'm saying now you take a point here, like 3, and you have a sequence of surfaces so that the slope goes to that point. Okay, I'm talking about really limit points. Okay, say now that we pass from simply connected to any group, we fix the fundamental group, and say that is going to be any group that is the fundamental group of some smooth projective variety. And at the end, that means any fundamental group of a surface by the Lefschetz hyperplane theorem, if you want. Okay, so I fix any examples. Pi 1, the fundamental group could be any finite group. So there are a lot of groups. Notice the difference with dimension 1, where we have this fixed infinite, well, except, well, infinite because G bigger or equal than 2. And now any finite group is possible for higher dimensions. Or any ball quotient group. You can take a ball quotient group and fix it. But of course, not any group. There are some restrictions. For example, the first Betti number has to be even because of the Hodge decomposition. So what we know, and what is the theorem here? So we know here, so again, you have 1/5 to 3. The theorem is that if you fix the group, so let me go directly to the theorem, 2020, Troncoso and me. Troncoso was my PhD student a year ago. If you fix G, then you have density, so complete freedom between 1 and 3. So like in the simply connected case, but now from 1 to 3. Now for lower slopes, in this case, we have some restrictions. So for example, using some results of Pardini, Mendes Lopez, if the fundamental group is finite, then the order is very restricted. at most 9, if you are between 1/5 and 3. So we cannot expect complete freedom for low slopes. There is also a conjecture by Miles-Reed for this other interval. So if C1 square smaller, strictly smaller than 1/2 C2, then he expects that the fundamental group is finite, or is like, I can explain you if you want later, the fundamental group of a curve is kind of comparable to the fundamental group of a curve. We don't know that is a conjecture. And it's optimal because there is an example, as I mentioned here, by Kuhn in his PhD thesis, actually, where that doesn't fit the picture of Miles-Reed. And then we have this unknown zone, which we cannot explore, although we have a machinery to try to answer this question. We don't know how to go lower than 1. Okay, that is the. So what about geography of rigid surfaces? And so now I will put some extra conditions and see what we know using the slope only. So we don't know anything about density. We don't have any interval which is dense, I think. But we have several accumulation points, and work by me and Stover, 2019, shows the first example where the accumulation point is 3. So we have a sequence of rigid surfaces where the slope goes to 3. And well, there are many, so all Boyle quotients are here, irreducible by these quotients, Boyle surfaces. Here, there are works by Catanese, Bauer, and Bauer-Pignatelli with these rigid surfaces that are not infinitesimally rigid, kind of recent work. Hirsenbruch, Kummer, covers also appear. Su, for example, has constructed proved that one of these surfaces were rigid, and then was taken by Bauer and Catanese, recent paper. Well, there are many examples. We don't know about density. It would be nice to know maybe a bit more. Kind of, we don't know much about these rigid surfaces. What about hyperbolic plus, for example, fixed fundamental group? So let me show the picture here. So I have 1/5 and 3, and we had the conjecture in the same paper with Troncoso that it might be possible to prove that they are dense hyperbolic in 1/3, and with the fundamental group of any hyperbolic surface that you want to fix. So the technique that we use would allow to prove that if you can prove a small technical detail that appears in the paper at the end of that paper, which is available in the archive. Well, there are many examples. Here is the Bogomolov zone, which are kind of quasi-hyperbolic, right? On the right, and then on the left, there are many examples. And I also have a work with Garcia Fritz, 2018, in relation to complete intersections. And we prove that all degrees of complete intersections, all multi-degrees for Pn n bigger or equal than 10 is possible by a hyperbolic surface. But we couldn't see what is going on for example, 2, 2, 2 in P9, P8, P7. That is one of the questions we have at the end of the paper. And to finish, we also have these. So what about canonical class samples? So there are no -2 curves in the surface and fixed fundamental group. So for example, I can tell you that for simply connected surfaces, the construction creates a lot of -2 curves in these surfaces. So we cannot answer this question for this part, high slope. So we don't know. But the similar detail that I was telling you about in here to solve this conjecture applies to this other one. So it might be possible to prove using that they are actually dense between 1 and 3 for any fundamental group, fixed fundamental group. Okay, that was my talk. 30 minutes.
Let's thank you. Are there any question or comment?
I'm actually about the projective models of these surfaces, like their embeddings and stuff.
Projective models for which surfaces? For the ones we...
Well, any of these surfaces that you're talking about that give you the density and things like this. Do you understand like what are various embeddings of these surfaces and projective?
No, not at all. No, they are kind of very abstractly constructed. No, I don't know how to show you these surfaces in some projective space. I have never tried. No, I don't know.
I have a question too.
Mm-hmm.
So at the beginning, you're talking about the line arrangements.
Yes.
So there's this notion of the free arrangement, and there's also situations in which the logarithmic tangent sheaf is stable. Does that have anything to do with your classification? And
no, I haven't tried any connection with that. I am aware of that, but I haven't tried. Even when this sheaf is not a vector bundle, right? When you just take that in P2, yeah, I don't know. I don't know if there are any connections. It would be nice to know.
Okay.
Yeah. I don't know.
And also, you said something about the surfaces of low multi-degree in PN. I didn't get exactly what was the problem that you were interested in.
So the problem was to show explicit examples of hyperbolic surfaces, which are complete intersections, but for low degrees, because they are not so easy to construct as far as I know. So for example, in P, maybe he said, in P3, it's still an open question if there are hyperbolic quintics, right?
No, we solved that. They are the very general one is well, it depends what kind of hyperbolic. Algebraic.
Brody hyperbolic.
That I don't know. That I don't know.
And it seems like it's the only case that is missing, right?
Yeah, I mean, that I don't know.
And so we provided like explicit construction for complete intersections, starting with P10 for all multi-degrees. For high multi-degrees, I think that there are ways to do it.
Are there more questions or comments?
Maybe I have a question. When you mentioned your paper by you and your student, you mentioned an unknown zone. I mean, a part where nothing was known. So my question is, what do you think it may happen there?
Between 1/2 and 1? Yeah, I have no. It's kind of hard to say.
But are there any examples in that part? Are there any examples?
Yeah, there are many examples. But for example, by Persson and Chen, which I mentioned for simply connected surfaces, constructed many, because we need accumulation points with simply connected surfaces to use our machinery. But and we do have all the way here. There are many, but they don't work for the machine we have, and where they shouldn't work in general, because here it's impossible to get any group. But they are there, and they just don't work. To tell you exactly what is going on, I would need to go to the construction and tell you what the things are not working. But
Thank you.
So I would like to know more accumulation points in this zone for simply connected surfaces. to try the machine.
More questions or comments? If not, let's thank again Giancarlo.
Thank you.